One of the reasons that we look at things like transition metals, and later on we'll look at the properties of the S and the P block elements, is it provides a way for us to apply and expand and think about concepts that we've looked at before. So before I get really into the special chemistry of coordination chemistry, it's kind of nice to go and look at some of the properties of transition metals that we can think back to properties that we studied before. And one of those is atomic radii. If you think generally, atomic radii decrease as one goes across the periodic table. And you can certainly kind of see that here if we start off with scandium, 164 picometers, and then going down to 147, 135, 129, whoops, up to 137, but then 126, 125, 25, whoop, going up again, and so on. Now, if we plot that out, we can see that little sort of spike there at number 5, the triad number 5, which is manganese. And we'll talk about manganese in the next slide, looking at the electron configurations. But manganese is kind of special. And then we're swooping up again here with copper and zinc. And as we'll see again in a minute, their electron configurations are rather special. I put in, and this is the last time we're going to worry about the second and the third rows, the second and the third rows radii, because it's rather interesting. You expect atomic radii to increase as you go down the periodic table, and certainly 164, 178, 187. But after that, if we plot out those radii in yellow, there is the second row of the transition metals, and then in green is the third row. And you can see after you've done the scandium, yttrium, lanthanum, they're almost identical. Now this is because once you get past lanthanum, in here are of course the F block. Okay, going between lanthanum and hafnium, you've got the F block kicking around in there. And so that has a massive effect in terms of shielding, in terms of changing the chemistry and so on, so that effectively the second row and the third row have pretty close to identical sizes and pretty close to identical chemistry. And this is something called the Lanthanide Contraction. Okay, now I'm not going to dwell on that any further, but if as you go on in your chemistry somebody says a lanthanide contraction, what it is that because of the lanthanides kicking in here after lanthanum and hafnium, the chemistry, the size, everything really in so many ways about the second and the third row of the transition metals pretty much the same. They have the same radii, they have the same electron configuration, they have very, very similar chemistry. So for most of the rest of this little video series, I'm going to focus on the first row metals: scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. And before I actually get into it, I'm going to share a little thing that I think is kind of silly. I don't like generally those mnemonics, those memory devices for teaching. I would far rather that people understand things rather than need that little memory cutesy-poo phrase. I mean, oil rig, for example, right? Oxidation is lost, reduction is gain. That's great the first couple of times you encounter oxidation and reduction, but after a while it should just become so ingrained in you, you don't need that little memory device. And sometimes they get even stupider. I mean, Leo the lion goes grrr is another equivalent of oil rig, right? Leo, loss of electrons is oxidation, and grrr, gain of electrons is reduction. But that's just absolutely goofy. Anyway, on the subject of thorough goofiness that has stuck with me since 1981 was my girlfriend back then had a mnemonic for remembering the first row of the transition metals, right? And it was Scottish TV, crummy, Facconi, Cousin. Okay, and that's how she remembered it. And it makes no sense at all, right? Scottish TV, crummy, Facconi, Cousin, but it stuck with me all those years. And I will acknowledge that every so often when I'm writing out the periodic table, and by this stage I've used so much of the periodic table that I can just sit down and write it out, except for the actinides and those newer post-uranium or trans-uranium elements. I just sit down and write it out any old time you want, but I will occasionally check myself with Scottish TV, crummy, Facconi, Cousin. Anyway, so first row is what we're going to focus on. Now, before again we get into a lot of the specific chemistry of the first row of the transition metals, it is again worthwhile going back and applying some earlier concepts. And in the last slide, we looked at atomic radii. And of course, when you first encountered atomic radii, it was after we thought about electron configurations. So here's the electron configuration of the atom. So scandium, no problem. We're moving from the 4s2 into the 3D. So we go 3D1, 3D2, 3D3. And then if you remember, chromium should be 4s2, 3D4. But because of the extra stability of that half-filled d subshell, we bump one of the s electrons into the 3D. So we get 3D5. Manganese, remember that peak at the atomic radii was manganese. There's that 3D5 super duper special extra wonderfulness of the half-filled d subshell. And then we get 6, 7, 8. Copper again, another exception, should be 4s2, 3D9. But because of the super duper nature of a filled d subshell, we pop one of the electrons up into the d. Now, if I look at the M+, so this is just taking the atom and removing an electron. And of course, that electron comes from the 4s rather than a 3D. So you can see again the 3D pattern, the same 1, 2, 3, 5, 5, 6, 7, 8, 10, 10. But now instead of it being 4s 2, 2, 2, 1, 2, 2, 2, 2, 2, 1, 2, it's 4s 1, 1, 1, 0, 1, 1, 1, 1, 1, 0, 1. Okay, nothing really special though about any of those electron configurations. Comparatively, all we're doing is pulling out one of those s electrons. So if we plot out the ionization energies, there it is, pretty much increasing as we go from left to right, as we expect generally in terms of ionization energies. However, the fun starts when we start looking at the second ionization energy, and that's the energy needed to go from the 1+ to the 2+. We're pulling out another electron. Now, of course, here we're going pulling it out of the s, pulling out the s, pulling out the s, but now here for chromium, we've got to pull it out of the d. And not just out of the d, but out of a half-filled d subshell. And so when we plot those out, there is that little spike there, that little hump up for chromium, okay, as we go scandium, titanium, vanadium, 1400, 1591, then back down to 1509, okay? And that's because we are going from a D5 to a D4. Now we see another hump as we go along up here for copper. Okay, we go 1700, 1960, 1733. Okay, and so that is because, again, we're pulling an electron out of something special. We're pulling an electron out of the filled d subshell, trying to get to an unfilled d subshell. So you can see that we see those same little trends, those same peaks, although not massively huge peaks here, but there's certainly peaks there that we would expect, and we can hark back to our first studies on ionization energy and relate that to nitrogen was big because it had that special half-filled P. And then, of course, we got to neon, and that was super big. And previously, before that, we said that beryllium that had that filled 4s was higher than it should be, and boron was lower than it should be. So the half-filled and the filled d subshells here, we can see the effects in terms of the ionization energies, and we can relate those ionization energies back to the electron configuration. Now let's go one more and look at the third ionization energy. So that's associated with pulling an electron out of the 2+ to get to the 3+. And if I plot it out, you can again see there is a definitive spike and then a definite drop. I mean, it's not just a spike and a little bit here, but it's a spike and a big drop. Well, let's see what those are associated with. This first one's associated with manganese. Okay, and you can see we went to 3000 up to 3200, back down to even less than we were before. Okay, so the sort of golden, dark golden one there is manganese. There again, we're going from a half-filled D to a not half-filled D. Okay, so big spike there because of the manganese. But now for the first time, we're seeing a significant drop down here. And that is associated with iron. So there we go. And this is the first time that we actually see making the half-filled D is actually of a significant energy stabilization. Iron 2 is 3d6 and 3 is 3d5, and there you see that big drop here that I've circled in the purple, associated with making the D5. So ionization energies, interesting to look at, to think about the relationship between electron configuration. We see big humps in when you're breaking a D5. We see another big hump here in which we're breaking a D10. And then we also see a particularly big drop in which we are making a D5. Now, some of you will have said, well, why haven't we got a big, massive one up here for zinc? Because with zinc, we're breaking into that D10. And you can see that zinc is higher than it should be in terms of a nice little straight line, but not significantly so. And to be perfectly honest, I don't really understand why that is. Okay, zinc is, I mean, it's a pretty big jump. You're going from 900 to 1700 up to 3800 to pull this one away, but it's not sort of up there as I thought, or some people might have thought it was. Certainly it's an increase because of breaking into the 3D10 going to the 3D9. Not a significant increase, but one to at least mull upon to a certain extent. So studying atomic radii, rather interesting, Lanthanide contraction to point out, and then just a reminder of our electron configurations. The metals start off with the 4s's. You pull out those 4s electrons before you start pulling out the 3d electrons. And of course, reminding you of our cation discussions going back, all of the transition metals except scandium have a nice 2+ cation as part of their chemistry, which again we explained well back then in terms of electron configurations. Last topic to recap / refresh is that of oxidation states. I hope you remember when we were talking about electron configurations and then we moved into ion formation, that while, for example, the alkali metals will only make +1 cations because after they've lost that one electron, they're in a noble gas configuration, transition metals can have multiple different cations because they're losing those d electrons. And indeed, you can have transition metals with up to +7 for an oxidation state. Now, you might also remember, and I've mentioned this a couple of times already in this little lecture series, the difference between the early transition metals, that's scandium through manganese or Scottish to be crummy, and then the later transition metals, that's for iron through zinc, Ficoni, Cusin. Okay, when we're thinking about the early transition metals, they can lose as many electrons up to getting a noble gas configuration. So thus, for example, scandium will lose 3 electrons, the 2s and the d. Once it loses that, it's got the electron configuration of argon. Titanium can lose all 4 of those electrons to give you titanium 4+. They're not only the 2 in the s subshell, but the 2 in the d. Vanadium can make vanadium 5. Chromium can make chromium 6, and manganese can get all the way up to manganese 7. Permanganate ions feature manganese 7, that's MnO4-. Chromium, of course, chromium 6, we talked about that a lot when we were oxidizing alcohols. Chromate CrO4 2- is chromium 6+. Dichromate Cr2O7 2- is chromium 6+. So for the early transition metals, you can have oxidation state where they've lost every single one of their electrons past the previous noble gas. However, you can then have other ones as well. Scandium you only ever see commonly as 3+, but you can have titanium 2+, that's losing those s electrons. Vanadium 2+, that's losing those s electrons. Chromium 2+, that's losing the s electrons, even though of course it only has one of them, pulling another one out of there. And manganese 2+ is a very common oxidation state of manganese because that's where it's lost the 2+ and you're left with the half-filled D. But you can also have 3+. Titanium 3+, quite happy, losing both of the S's and one of the D's. Vanadium, you can have 3+ and 4+, so that's losing both of the S's and one D and then a second D to get to the 4+. Chromium, you see extensively as 3+ to go along with the 6+, but you can see chromium 4 and chromium 5. And manganese, very happy to have 4+, 3+ slightly less so. You can see 6+ and 5+ even. The crosses are ones that you can see, but they're not hugely common. The ticks are ones that you see and are common. So lots and lots and lots of oxidation states available to the early transition metals, and it's going to be important that you can recognize which oxidation state a particular metal is in. Okay, now once we get past manganese and into the later transition metals, they all quite happily make the 2+ cation that you expect from having the 2s electrons there, but then in many cases that's it. Iron can lose a 3rd electron, and of course if iron loses a 3rd electron it's D5, so that's half filled. Cobalt can quite happily make cobalt 3+ and 2+. The 3+ is we've lost both of the S's and one of the D's, so it's got a D6 configuration, and you'll see in a later movie why D6 is not a disgusting thing to have under certain conditions, but it can't lose that 4th one to get down to D5. Nickel you'll only ever see as 2+. Zinc you will only ever see as 2+. Zinc, of course, easy to rationalize that because once it loses those 2 electrons, you have the filled D subshell. Copper, you should remember this from your studies, copper 2+, very common, and then an extensive chemistry of copper 1+, and that's where it's just lost that 1s electron and you have the filled D subshell. So, very, very important that you're aware of the oxidation state that you're discussing for a particular transition metal, because unless you're talking about scandium, nickel or tin, there could be more than one possible oxidation states. So anyway, there's a 4-slide recap of some important chemistry, harking back to our study of electron configurations, things that you needed to see. Important you're aware of the atomic radius and particularly the Lanthanide contraction for later chemistry studies, but then important you also really appreciate the effect electron configuration has as studied by ionization potentials and as shown and manifested by the different oxidation states available.